Dear students, in this lesson we are going to talk about valence bond theory and hybridization. The concept of orbital hybridization first introduced by Linus Pauling from his book Nature of the Chemical Bond. Now let's discuss what is the basic idea of valence bond theory. Assume there are two atoms. This is nuclei of one atom and this is nuclei of another atom, and there are orbitals. This is one orbital. This electron can exist, and this is another orbital of this atom where this electron can exist. An orbital is a mathematical function describe the location of electron can exist. Therefore, these two half-filled orbitals overlap to form a covalent bond. The electrons in this new probability density are then shared by both atoms. This is two atom nuclei, and this is our new electrons probability density location. Now these two electrons in the new location, they are arranged themselves to have maximum overlap of their half-filled orbitals, producing a bonding orbital of lowest energy. We call this as a bonding orbital. All forms covalent bonds, and all overlapping orbitals must be half-filled, or orbital with paired electrons can overlap with an orbital with no electron. The previous example is half-filled orbital, and next example I will think about, this is one orbital where two electrons exist, and this is another orbital. There are no electron exist in the orbital. Therefore, these two orbitals can overlap together to form new bonding orbital, and these two electrons can exist around this new location. We call this is new bonding orbital, and the new probability distribution form can only have a maximum 2 electrons. There are no more than 2 electrons. Orbitals can overlap in two main ways, creating two different type of covalent bonds. One is sigma bonds, another one is pi bond. When consider sigma bonds, there are two atoms. Think about, this is one nuclei of, this is another nuclei of one atom. These two combine together to form this kind of new orbital where these two electrons exist between the nuclei of the overlapping atoms. These are the example of sigma bonds. Think about two hydrogen atom overlapping of s orbitals of these two hydrogen atoms to form new H2 molecule, and also this is fluorine atoms, two fluorine atoms combine together to form F2 molecule. This is p orbital overlapping. In hydrogen there are two s orbitals overlapping, therefore we call s overlapping. And next thing is the pi bond. In pi bond, electron densities are above and below the nuclei of the bonding atoms. For example, as shown in this figure, this is the nuclei, this is the nuclei. when these type of two atoms combine together, above or below electrons can exist. Those type of bonds we call pi bonds. In the sigma bonds, they have in between the atoms, but here this line above the line of two nuclei or below the nuclei. If there are double bond, there should have only one sigma bond between two atoms. Therefore, other bond should be pi bond. You can see the overlapping of sigma bond and pi bond using same atoms. There are two carbon atoms, one is here, other one is there. When there are, as you know, there are 3 s orbitals, 2 s orbitals can overlap in between two atoms, and other two can overlap on top of this line and the below of this line. This type of bond we call pi bond, and this one we have sigma bond, and these two electrons exist in a pi bond. When you talk about triple bond, there are only one sigma bond, as you know, because there are only one line you can draw between two nuclei of the atoms. Therefore, in a triple bond, other two bonds should be pi bonds. Here, this is the example of carbon, one carbon, another carbon atom. These two carbon atoms combined together using s orbitals. One s orbital can form one sigma bond, and other and above this plane and below this plane and side of this carbon and other side of this two carbon. Therefore, the total appearance of the electron existence like this. Therefore, two electrons can exist in this sigma bond, and other two electrons can exist in one pi orbital, and other two can exist in this pi orbital. One special term you should know in this lesson is excitation. The most of the time atoms exist in their ground state. That means lowest energy level, as we know in our electronic configurations. But in certain cases, the instant before bonding promotion to higher energy level take place, allowing more bonding spaces. For example, as shown in this figure, as you know, in your electronic configurations, this carbon atom, let's assume carbon atom can exist this kind of electronic configuration. This is 1s2 and 2s2 and 2p2. So, promoting this one electron of s2 to this point, as shown in the below figure, you can say this is an excitation of electron. Now you have 4 half-filled orbitals. Therefore, you can form 4 bonds. Before the excitation, you can form only 2 bonds because there are only 2 half-filled orbitals. Hybridization is the next important parameter when you are talking about bonding. As shown in this figure, combining of this s orbital with p orbital, you can form a new orbital we call sp hybrid orbitals. the merging orbitals must be half filled. Therefore, this should be half filled and this is half filled. Then you can form this kind of sp orbitals, and this one also half filled orbitals. Therefore, when no orbitals are lost due to merging, therefore they should have two number of this kind of new sp orbitals. Mix at least two non-equivalent atomic orbitals, for example s and p. Hybrid orbitals have different shape from original atomic orbitals. Now you know what is the original shape of s, p, d, f like orbitals, but hybrid orbitals have different shapes than these original shapes. Covalent bonds are formed by overlap of hybrid orbitals with atomic orbitals or overlap of hybrid orbitals with other hybrid orbitals. Therefore, there may have two type of bonds. Let's consider sp3 orbitals. How these sp3 orbitals, when we consider sp3 hybridization, it's better to consider the electron filling stage for carbon. In carbon, as you know, there are 1s electrons, there are 2 electrons, then 2s 2. There are 2 electrons in 2s, then another 1 electrons in 2p and another 1 electron in 2p orbitals. Then excitation of these electrons can make moving these electrons to the above unfilled orbital. In here, now it can fill to this point. Therefore, combining of these 4 orbitals together can form new 4 orbitals we call sp3. In this sp3 orbitals have same energy, but this is not energy lower than 2p and higher than 2s. This figure you can show every orbitals individually. This is s orbital, it's spherical, and this is 1 px orbital, and this is py orbital, and this is pz orbital. Combining of these 3 p orbitals plus 1 s orbital together to form 4 sp3 orbitals. For this 4 sp3 orbitals are shown in this figure. This figure shows the cross section of an sp3 orbital around the nuclei. Therefore, every dots interpret their probability around the nuclei. Here in this figure shown the sp3 hybridization of a carbon atom as we discussed in our previous slide. Therefore, you can see this is p orbital and this is s orbital, and 1s and 3p orbitals together to form this kind of 4 sp3 orbitals. For methane, 4 equivalent CH sigma bonds can be made by the interaction of sp3 of carbon atom with the s of hydrogen atoms. Therefore, hydrogens can attach around 4 areas to form methane. Next, sp2 orbital. This is the shape of sp2 orbital. Let's discuss this in detail. Now let's discuss an energy level diagram showing the formation of 3 sp2 orbitals. For example, this is energy to upward, therefore there are 3 p orbitals and 1 s orbitals as shown in this figure. Combining of this 1 s orbital and 2p orbitals together, and hybridization take place to form 3 sp2 orbitals. Therefore, the energy of this 3 sp2 has more towards s than sp3. Therefore, this energy different E is, think about, its sp2 is higher with compared to this energy in sp3. Then let's consider the shape of sp2 orbitals. In the previous example, as you know, there are unhybrid p orbital and there are 3 sp2 hybrid orbitals. Therefore, this orbital, the shape should be planar. Therefore, think about 2 p orbitals are exist in single plane. Think about there are 2 planes, x and y axis. Therefore, px and py combined with s orbital to form sp2 orbitals. Therefore, these 3 new sp2 orbitals are exist in xy plane. Let's discuss how to form BF3 molecule. For BF3 molecule, as you know, boron is the center atom and there are 3 fluorine atoms around boron. Boron has only 3 electrons and fluorine 7. Therefore, this boron should have 3 electrons, unpaired electrons to form 3 bonds with fluorine. Therefore, this is the ground state of boron atom. To form 3 bonds with fluorine, there should have 3 unpaired orbitals. Therefore, this electron should excite. Therefore, now we have 3 unpaired electrons. But those 3 orbitals have different energies. Therefore, these 3 orbitals should combine together to form similar energy orbitals. We call combining with 2p orbitals and 1s orbital, we can form sp2 hybrid orbitals. There are 3 sp2 hybrid orbitals we can form, and therefore 1 unpaired orbital remaining. This is the shape of sp2 hybrid orbital. Before hybridization, they should have 2 p orbitals and 1 s orbital. Therefore, combining of this s orbital and this, let's think px, and this is py, these 3 orbitals combine together to form these another 3 orbitals we call sp2. This is also 1 sp2 orbital, this is also 1 sp2 orbital. Therefore, these 3 are exist in the same plane, that is the most important thing, because this all sp2 orbital should have in xy plane. Therefore, this is the final shape of BF3 molecule, as you can see in the top view. Now let's consider another example, sp2 hybridization of a carbon atom. Here some different than boron, because there are another 1 electron higher than boron. Therefore, when 1 electron excite to higher p orbital, there may have 4 unfilled orbitals. Therefore, when it want to form 3 bonds with 3 atoms, they want to make hybridization for 2 p orbital and 1 s orbital, because they want to hybrid the lowest energy orbitals. Therefore, 1 s orbital and 2 p orbitals hybrid. Then what happened after this hybridization? There are 3 orbitals are there, sp2 orbitals are there, and there are remaining unhybrid p orbital is there. Therefore, when it form hybrid orbitals, this is the shape, and the angle between 2 sp2 orbitals is 120 degree. And then let's consider all other orbitals. There are remaining another unhybrid orbital. Therefore, these electrons are existing these 3 and 4 orbitals. Example of formation of sp2 hybridized orbital in carbon is ethylene. The Lewis structure for ethylene is here. This is the Lewis structure of ethylene. Then let's consider how these 2 carbon atoms together combine using this hybridized orbital. Here, this hybridized orbital, these electrons in this hybridized orbital and this hybrid orbital combine together to form this overlap orbitals. Therefore, we call this is bonding orbital. Therefore, in between this bonding orbital, there are 2 electrons and another s orbital from hydrogen with 1 electron from this hybrid orbital can overlap together to form another bonding orbital. This is this one. So previous one is this one. Therefore, this is a sigma bond. Same as this is a sigma bond, and this is a sigma bond, and this is also a sigma bond. But then this is unhybrid p orbital, and this unhybrid another p orbital. There combination of these 2 on top of and the bottom of this sigma bond, we call they have pi bond. So therefore, the second bond of ethylene is a pi bond. Therefore, 2 bonds means one is sigma, another one is pi bond. Now you can see in these 2 images to better understand about how these hybrid orbitals and overlap orbitals and pi orbitals exist in three-dimensional arrangement. This is the image from top view of ethylene molecule. Therefore, you can see these 4 hydrogen atoms and 2 carbon atoms are exist in same plane. Next important hybridization is sp. Here you can see the shape of sp orbitals. Now let's discuss the formation of sp hybrid orbitals. This is similar to the formation of sp3, sp2, same, and here there should have hybridization of one s orbital and one p orbital. Therefore, after formation, these are the 2 sp orbital and there are another 2 unhybrid p orbital. There are unhybrid p orbital. As you can see, there are no energy change in these 2. Let's see, when s and p orbital hybridize, they should have this kind of 2 hybrid sp orbitals. Therefore, angle between these 2 hybridized orbitals are 180 degrees. How to form beryllium chloride? In beryllium chloride, beryllium molecule should have 2 chlorine atoms in both sides. Therefore, beryllium should have 2 bonds. This is the electronic configuration of beryllium. There are only 2 s electrons. Therefore, to form 2 bonds in beryllium, this electron should excite. Therefore, now excited state. Then these 2 orbitals should hybridize to form 2 bonds. Therefore, they have 2 hybrid orbitals and there are 2 unhybrid p orbitals, but electrons are existing hybrid orbitals. This is the shape of sp orbitals and hybridized sp orbitals. Here this is s orbital and this is p orbital and this is sp orbital and this is another sp orbital. This is only existing towards x-axis. Therefore, this is linear, and beryllium chloride, the shape is linear. Therefore, you can write down Cl to this Cl, you can write down a line we call linear shape. Consider another example of sp2 hybridization in a carbon atom. This is not like actually the barium atom, because beryllium has only 2 electrons. Therefore, in carbon there are another 2 electrons exist. Therefore, when as usually then it is excited, there are 4 unpaired electron orbitals. Therefore, after hybridization of these 2, there may have sp hybridized orbitals with 2 electrons, and also there are 2 unhybrid p orbitals with electrons. That is the shape of these sp hybridized orbitals in carbon atom. Therefore, electrons are exist in this hybridized orbital and this hybridized orbital, and also this unhybrid orbital, and also in this unhybrid orbital. Therefore, there are 4 electrons are there. Now then let's consider acetylene molecule. For acetylene molecule, there are 2 carbon atom, and there are triple bond, and there are 2 hydrogen atom as shown in this Lewis structure. Therefore, this kind of sp, this is one sp orbital and this is another sp orbital of this carbon. There are 2 sp orbitals, and this is one sp orbital, and this is one electron in the sp orbital in this carbon atom. Therefore, then these 2 combine to form one sigma bond, and also this s orbital and this s orbital, and these 2 also can form another sigma bond, and this also can form another sigma bond. So okay, so then what happened to remaining unhybrid 2 p orbitals? They also should have to overlap together to form unhybrid p orbital to form pi bonds. Therefore, there are 2 pi bonds. They are forming, one is above the plane of this sigma bond, and other pi orbital form both side of this single sigma bond. Therefore, there may have pi bonds using unhybrid orbitals in carbon. Now let's consider another example to understand this hybridization. This is carbon dioxide. In carbon dioxide, only one carbon atom combined with 2 oxygen, and when you write down the Lewis structure, this is the Lewis structure. Therefore, when you consider this carbon, there should have 2 sigma bonds between 2 oxygens, and oxygen there may have sp2 hybridization. Let's consider how this oxygen fill in their valence electrons. As you know, there are 6 electrons in the final energy level in oxygen. Therefore, 1, 2, 3, 4, 5, and 6 electrons in the oxygen atom. Therefore, when this oxygen atom want to hybridize into sp2 hybridization, then these circled orbitals are hybridized into sp2 to form bonds with carbon. Therefore, this is the final structure, final shape of the sp2 hybridized oxygen molecule. However, when you consider this molecule, the electrons in this has only 1 electron, and this unhybrid p has 1 electrons. Therefore, and this one hybrid orbital should have 2, and other one also have 2 electrons. Therefore, then you can understand when I am filling these electrons in the given 3-dimensional shape. This has only 1, this has only 1, and this has paired electrons. Therefore, these paired electron orbitals are not involved in bonds. only unpaired electrons are involved in bonding. Therefore, when you consider the carbon should have now this kind of sp hybridization to form two sigma bonds with oxygen. Therefore, let's consider the three-dimensional arrangement in this carbon dioxide structure. This is the three-dimensional arrangement of carbon dioxide structure only considering hybrid orbitals. Okay, this is only considering the hybrid orbitals. Therefore, one electron from the hybrid carbon and another one in hybrid carbon, and here one in this hybrid sp2 and one in this hybrid sp2, and other oxygen molecules has paired electrons. Therefore, this one not involving bonds and this one also not involving bonds. Therefore, this two carbon and hydrogen oxygen can form sigma bond, and this again carbon and oxygen form sigma bond. Therefore, this two sigma bonds they are formed, and remaining unhybrid, this is unhybrid orbital and this is also unhybrid orbital. And as you know, in oxygen also contains unhybrid orbital and this oxygen also contains unhybrid orbital. Therefore, they can form pi bond between these two and another pi bond with this another two unpaired unhybrid p orbitals. Therefore, this is the shape. Therefore, in here this is one is sigma bond, one is sigma bond, and other one is pi bond, and other bond is pi bond. And as you can draw similar pattern, and this is example for N2 molecules, you can understand by referring this kind of more examples. As you know, when we want to form 4 bonds, we know there are sp3 hybridization. When we want to form 3 bonds, we can form sp2 hybridization. And if one molecule want to form 2 bonds, they can hybridize into sp hybridization. But how to generate more than 4 bonds? Remember this PCl5 SF6, like there are several molecules which contains more than 4 bonds in central atom, and the SN3P can generate only 4 orbitals. Therefore, to form more than 4 bonds, there should have d orbitals to generate. Let's consider similar to sp2 hybridization. There may, if you want to form 5 bonds, there may have sp3d hybridization. And this is example. You can refer this example and study more. And this is the structure of PCl5 molecules, and you can learn more by deep study of this kind of sp3 dehybridization. And if you want to form 6 bonds, you have to hybridize one s, 3p, and another 2 d orbitals to form similar 6 bonds. Discuss valence shell electron pair repulsion theory or Vesper theory. In the molecular level world, we can't see the world shape and anything using any microscope, because they are very tiny, even we can't see to our naked eye or even a microscope using light. But we can understand what are those shapes and those things using this kind of theory. Here, the basic concept in the theory is electron pairs repel each other. This applies to bonding pairs and lone pairs. As you know now, bonding pairs means they have sigma bond or pi bond. Or lone pair means they may have electron pair without participating to bonding, as we discussed in our previous examples. Then steps in applying Vesper theory. First, draw the Lewis structure, then count atoms and lone pairs and arrange them as far apart as possible, and then determine the name of the geometry based only on the atoms. Then we can understand what are the shapes of molecules. Here, as you know, then electron groups may have repulsion each other. Then think about, if you have 3 electron pairs, definitely you have to form this kind of 3, you have to form this kind of shape. Therefore, you can write molecules in these 3 points. This is the central atom. There's only these 3 electron pairs are there in central atom. You can understand what is the shape of this molecule. Then you can see this is trigonal shape. Therefore, that is the way you have to understand the shape of the molecule. Let's get some another examples to understand more. Understand more about the shape of molecules using these examples. Here, this is carbon dioxide. As you know, here only 2 sigma bonds between this central atom. Therefore, there are only 2 sigma bonds between carbon, and there are no more electron pairs. Therefore, we can say this is linear, and this is the 3-dimensional images. And next thing, if there are 3 sigma bonds between this central atom and there are no more electron pairs, then we can say this is the shape is planar, triangular or trigonal. And if there are 4 sigma bonds between around this central atom, we can say the shape of this molecule is tetrahedral. And another, there are 5 bonds and 5 molecules around the central atom, as you can see in PCl5, and you can see the 3-dimensional shapes also, and we call this as a trigonal bipyramidal. And next thing, if there are 6 sigma bonds around central atom, as in SF6, and 6 atoms around this central atom, then the shape we call octahedral. Now let's consider some complications to Vesper theory. Here there are some molecules which contains lone pairs in the central atom. These lone pairs are count for arranging electrons but not for naming the geometry of the molecule. Example for ammonia molecule. This is the Lewis structure of ammonia. As you know, in the central atom is nitrogen, and in the Lewis structure there are lone pair and there are 3 bonding electron pairs. When you write down the electronic configuration of nitrogen, there may have 5 electrons in the ground state. So then 1, 2, 3, 4, 5. Therefore, if there are sp3 hybridization, these all 4 orbitals should hybridize. Therefore, when you consider these hybridized orbitals, the shape we call tetrahedral shape in this molecular orbital arrangement. Then here 1 electron and 1 electron and another 2 electron, as you know in this after hybridization also there may have paired electron orbital in the hybridized orbitals. Then only this unpaired electron orbitals can make bonds with hydrogen. Therefore, remaining paired electrons, 2 electrons, are not involving bonds. Therefore, we can consider the shape of this molecule only due to the shape of atoms. Therefore, we call this shape as trigonal pyramidal. Therefore, due to the lone pair, the shape of the molecule we consider as a different name. Another important thing we should consider, the lone pairs are larger than bonding pairs. Therefore, adjustment of these geometries are changed. For example, in these angles, for methane there are 4 bonds, all are bonding orbitals, but in ammonia there are 3 bonding orbitals and 1 lone pair. And water molecule there are 3 lone pairs and 2 unpaired lone pair electron orbitals and 2 bonding orbitals. Therefore, due to the increment of lone pairs, the angle may be changed or decrease due to the more repulsion due to lone pair is higher than bonding pairs. Next important thing we have to discuss is lone pairs must be as far as possible. For example, let's consider XCF4 molecule. In here, as you know, Xc contain 8 electrons in their valence and 7 electrons in fluorine. Therefore, the total number of electrons are 36 electrons together with this Xc and 4 fluorine electrons. Therefore, when you write down the Lewis structure around Xc, 4 fluorine atoms you can draw, and here up to 1, 2, 3, 4, 5, 6 and 7, 8 electrons already gone for bonding. Therefore, remaining 28 electrons you have to fill in these molecules as lone pairs. Therefore, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Therefore, now 24 electrons will remaining 4 you have to put into the central atom Xc. Therefore, in the central atom, around the central atom, there may have 2 lone pairs and also 4 bonding electrons. When you write down, when you have this kind of 3-dimensional arrangement, you can put these lone pairs as shown in this figure. If you put this kind of arrangement, we call this shape of the molecule as seesaw. And also you can put like this. In this lone pairs, you can put as far as possible, as we discussed in this topic. If you put this type of lone pairs, then your molecular arrangement, we call this shape is square plane. Let's study all the names for examples of complicated Vesper geometries. For example, if there are only 2 orbitals, 2 bonding orbitals around one central atom, we call this as a linear. And there are 3 bonding around the central atom, we call planar trigonal. However, in this 3 electron pairs around the central atom, however, let's think one is lone pair, then we call this as a bent. The shape we call bent. Then there are 4 electron pairs around the central atom, we call tetrahedral. Tetrahedral shape. In this tetrahedral shape, think about one is lone pair and other 3 are bonding orbitals. Then we call this as a trigonal pyramid. And these 2 are bonding and other 2 are lone pairs, then we have to say this shape is bent shape. Now let's go to 4 electron pairs we discussed, and now let's consider 5 electrons pairs around the central atom. We call this as a, it's actually the 2 pyramids around this plane. We call therefore bipyramid. The base is trigonal, therefore trigonal bipyramid. In this 5 electron pairs around the central atom, but let's think only 4 are bonding and other one is lone pair, then we call this shape as seesaw shape. And there are only 3 bonding orbitals and other 2 are lone pairs, we call as similar to the second shape, planar trigonal. And there are only 2 bonding orbitals and other 3 are lone pairs, then we can say this is actually linear shape. And similarly, when we discuss 6 bonds, 6 electron pairs around the central atom. The shape, if there are all 6 are bonding orbitals, we call this shape as octahedral. Octahedral. And here also you can say if there are only 5 bonding and other one is lone pair, then we call this as a square pyramid. And we can say there are 4 bonding and other 2 are lone pairs, then we can say square shape. Then we can discuss more about these shapes. We should know this important shape definitely. Then you can learn more shapes in next 2 slides with the examples here. Therefore, you can refer your handouts and understand more about these shapes, and then you should know what are the shapes of molecules. Then first thing you have to draw your Lewis structure, and then you can understand what is the shape of your molecule. Before the conclusion of this lesson, I want to mention that you should have good knowledge how to draw a Lewis structure, and using the Lewis structure you should know what are those hybridization in the central atom, and you should know what are the shapes of electron pairs in the central atoms and the shape of those molecules. Please refer your handout, and also you can learn more about outside resources, and please practice more. Thank you very much for listening.